Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about a rotating coil in a uniform magnetic field. This is an IB question in which I've also attached some of my own questions in here for the sake of completion. It's just seeing all the variations of questions that could be thrown at you for this typical type of question. So let's get started. Here we have a coil rotating at a constant speed in a region of uniform magnetic field. The graph shows a variation with time of the EMF induced in the coil for one cycle of rotation. On the graph, label with letter T a time at which the flux linkage in the coil is at a maximum. So I'm gonna draw a diagram here to help us explain why this is the case. So when the flux linkage is at a maximum, it means that if this is my coil, my magnetic field lines intersect it perpendicularly, directly perpendicularly like this, okay? So imagine you have a magnet that is you have a magnet that's into the page and a magnet outside the page, creating a magnetic field going into the page like this. This is going to achieve maximum flux, okay? Or if you think of it this way, if imagine that's my loop of coil. So imagine this is my loop of coil, and then we're looking on it at a side angle, okay? If we're looking at it in a side angle, then all of the magnetic field lines will be just going through it, so that the plane of my coil is perpendicular to my magnetic field. So that's when the flux linkage is a maximum. So how do we know which part of the graph that represents? Remember, the EMF, by definition, is the rate of change of your magnetic flux based off of Faraday's law. So that is directly proportional to the change, okay? So notice that having a maximum flux does not necessarily mean that the rate of change is the maximum. So there's a couple of ways where you can tackle this. The first one, which could be very simple, just looking at it mathematically, you do need the equation for that. So unfortunately, if you don't have the equation, it might be a little bit tougher to work it out. But essentially, you kind of have to work it out with the fact that the flux here is the magnetic field times the area, and the cosine theta is the one that is changing. So you're looking at how cosine theta is changing over time, assuming this is only one coil of wire or many. So there's one way to approach it. So that's change in angle there. So that's like it's doing a little bit of calculus and a little bit of math, which then the equation works out to be the EMF induced is going to be a function of sine theta. So that's one way you can approach it, which is very mathematical. I like to approach it a little bit more conceptual, because you might notice in your data booklet you're not going to have that. You have this equation, but you don't have the one that involves the EMF related to the sine theta. So let's just do something a little bit more conceptual. So we're going to touch on a little bit of motional EMF. So take a look at this coil and imagine electric field lines are going through it. I'm going to do a diagram, and kind of like the one I have over here, where you're looking on it at a side view. So I'm going to draw this here, and again, I'm going to show that imagine this is spinning, okay? So imagine that it's rotating. It is rotating by some external means, either by, say, either a hand shaft or some sort of mechanical shaft, which causes to kind of rotate around like this, okay? So imagine this is the axis here, so it's rotating around this axis, and these are the magnetic field lines that are going through it, okay? So imagine that thing is that blue line, which is kind of your side view of the coil, is rotating around, okay? So you kind of have to think of it this way. As this shaft is rotating around. Think about all of the charge carriers, which we'll call it. We'll use positive charge carriers because we're talking about conventional current. Of course, that's not the actual thing here. But imagine as this is being rotated, take a look at the direction of the velocity of these charges as it is sweeping through the magnetic field. So these will be the directions of the velocities at a single point. Okay, so kind of drawing them through like this. And according to this one, the induced EMF is directly proportional to the magnetic field times the length of the wire times the velocity that the particular charge or the particular charge of the wire is moving perpendicular to the field itself. So let's go around here. So take a look at this the top part of the coil. So you kind of have to think about that this part of the coil is actually going into the page. Okay, so this is the best I can do. I tried to compress this roll of tape, but I can't. So you're looking at this tape like this, okay? Looking at the side. And what it's doing is, imagine the field lines are going through it. So actually, it'd be this way for you if you're looking at it from a mirror side of the image. Imagine it is rotating this way. So it's rotating this way, which means this part of the coil is moving through, it's cutting through the lines and is going down. So if you work out the velocity of those charges using your right hand rule, okay, notice that the velocity of those charges as it's moving through the field is going to be perpendicular when the coil is about roughly around this position. So when it's doing this, the velocity of these charges perpendicular to the motion of these charges in relation to the magnetic field, this is where it's going to be the most perpendicular. So as the coil sweeps down like this, when the coil is in line, or it's about to be in line with the direction of the field, this is where it's going to achieve the maximum EMF, because the velocity of these charges in the coil is the most perpendicular. It's closer to 90 degrees to the direction of the magnetic field lines. Okay, so so that is this part. Where is it? So notice this part here. This velocity of these charges are perpendicular to these field lines, meaning the maximum EMF is achieved at that location. And this is when the flux linkage is actually the lowest. So let's mark it here. Maximum EMF, this is low flux linkage, okay? This is low as well, this is low, okay? Low flux, okay? The question was high flux, okay? When the coil is in this, is passing through it, is around roughly in this position. And when the coil is moving through this position, notice that the velocity of these charges would be moving relatively parallel with the magnetic field lines. So the EMF induced around this area is going to be the lowest. So this is actually where the maximum flux linkage is at. So at these positions here, either at 5 milliseconds or at 15 milliseconds. So either here or here is going to be where the coil is at a maximum. So if you actually really wanted to work this out, you can take a look at what's happening with the top coil here. Imagine it is actually a square, okay? So if the field is going towards the right, if the charges are going to be moving down, since this thing's, let's say, spinning in a clockwise direction, then the charge is going to move out of the page, meaning that the charge is going to move closer towards you. So the charge is going to move towards this end of the coil, and then it's going to move down down through the other end. Notice that the flat part of this coil, the blue line, that part of where you're seeing this part, there's not going to be any current. That part won't do anything in terms of generating the EMF or in terms of providing length of the coil, because no matter how it's moving, the movement of the charges won't be in a way so that it moves along the coil. Okay, so that's something you work it out. But essentially, I'm just using this bar of coil that's going into the page, and as that's sweeping through, the maximum EMF generated is when this velocity is perpendicular to the field when the coil is parallel, not when it's perpendicular for max flux linkage, which is why when the EMF is the smallest, that's when the change in the flux is the lowest, either at 5 or 15 milliseconds. Whew, okay. Long explanation. So, yes, it is much easier with the equation to explain it, but hopefully that also helps. Moving on. Use a graph to determine the rate of change of flux at t equals to 4 milliseconds. Let's use purple. Okay, so at 4 milliseconds, let's see, this is going to be 1, 2, 3, 4, so roughly here about 2. This is at 2 volts, okay? Use a graph to determine rate of flux change. So we know that the EMF is directly related to the change in the flux. Okay, that should be a squiggly line. So that is it. We don't have to do anything there. So this is going to be actually just 2 volts. Okay, 2 volts, or that's going to be 2 Weber per second. Okay, so first of all, you have to state that, and notice it is not the slope. It is, you might think it's the slope because it's, you're thinking of rate of change. But be careful, it's not the rate of change of the EMF is the rate of change in the flux. It's the rate of change in the flux gives you the EMF. So the EMF is the rate of change in the flux. So that's something we have to be careful about. So if I have to explain my answer, then I'm going to have to say something along the lines of the EMF gives me, or it's the rate of change in flux that gives me the EMF. So the EMF at 4 milliseconds must be my rate of change of flux, okay? So that's what my explanation would look like, okay? So next one, 3, calculate the root mean square value of the induced EMF, okay? So the EMF, we know its peak is at 6 volts. So writing that down gives me 6 volts, and we need to calculate the root mean square. We know that this is just the max, Vmax, divided by square root of 2 is going to give me the RMS voltage of the induced EMF. So taking 6 divided by root 2 gives me 4.24. Rounded to 2 sig figs, that's about 4.2 volts. Next one, question 3. The speed of rotation of the generator is halved with no other changes made. So this spinning coil is going to slow down. So if that's going to slow down, it's going to be halved. It means that each cycle is going to be each cycle is going to be longer, which means period is going to go up. In fact, it's going to be multiplied by 2. And assuming that the graph starts off at the peak, drawing this with red, let's use red. It's going to start here, and it's probably going to end somewhere over here, okay? Because that's going to give us exactly half of a period, okay? Or sorry, it's going to give us half of the period, which of course, since the period doubles, then half the period would take exactly 2 milliseconds, since the full period is 40 milliseconds. Okay, so that's the first thing. But we can't just draw everything in yet, because we also know something else. We know that the rate of change of the flux is directly proportional to the EMF. So since the generator slows down, the EMF induced will actually be lower, because the rate of change in the flux linkage is also halved as well. So my EMF is going to half, and it's going to be at half of 6 is going to be 3. So that's going to be right there. for where it starts, and then where it ends, it's going to be about there. So we can get rid of those big fat red dots because that's not going to be the case. Okay, so it will intersect the middle at 10, and we're going to curve this one out and draw this as best as we can. Okay, so there we go. So period is going to double and EMF is going to decrease by 2. Okay, awesome. Okay, keep going. A resistor resistance 25 ohms is connected across the output of the generator. And, we're going to assume that it hasn't halved yet. Okay, let's assume it hasn't halved. This is the part of question that I created. So I think, well, I just attached some other questions to it. So I might have to change a number here because I screwed up. I didn't give the right number for the time. But anyhow, ooh, maybe we could do that. Okay, so a resistor of resistance 25 ohms is connected. That's our R value. We want the RMS value of the current. So we actually have the RMS of the voltage already from the previous question. The RMS is 4.2 volts. It's actually 4.2426 ... volts. I'm going to use that instead. So the current, which is I RMS, is going to be equals to V RMS divided by the resistance. So 4.2 ... over 25 ohms. This is going to give us 0.1697. It's going to round up to 1 point, sorry, did I say 1 point? I meant 0 point. 0.17 amps. Okay, there we go. Okay, beautiful. We are going to continue with the average power dissipated in the resistor. So the average power, notice it's not the maximum power. The average power means that we're going to use the RMS values and not the peak values. So we know power is, and I like for a resistor just to use I squared R, or in this case, IRMS R, or that squared, which is going to be our current, and without any rounding, 0.17 ... actually that's 16 ... amps. Don't forget to square it, times your resistance. Okay. That is 0.72. 0.72 watts. Okay. Alright, and the last question is the power dissipated in the resistor at 0.4 milliseconds. 0.4 milliseconds. Yes, they wouldn't make sense. So guess what? I'm going to change this one, and since I made this question up as I'm going to change it to 40 milliseconds. Ho ho, 40 milliseconds. So there we go, 40 milliseconds. You might think, but 40 milliseconds isn't on the graph. But keep in mind that this is one full period. So after another period, the EMF is going to be back up at 6 volts again. So at t is equal to 40 milliseconds, the voltage or the EMF is going to be, was that 6? Yeah, 6 volts. So to calculate the power dissipated in the resistor at 40 milliseconds, EMF of 6 volts, assuming that's the only thing attached to the the generator, which is just that one resistor, then we can use power is equal to the voltage squared divided by the resistance. And since it wants the power dissipated at that time, I'm going to use the EMF at that time, the voltage, 6 volts. This is going to be squared divided by the resistor, the resistance, which is 25 ohms. And that's going to pop out a 1.44 watts. Okay? Which is less than the average. And less than the average. And interesting, and it kind of makes sense because this is exactly twice that of the average, and the average of power should be exactly 1/2. Exactly 1/2 of the total, with the peak. And 6 volts is exactly at the peak. So that was very helpful for that. But if the time was given at some other time other than a peak, we would have to use that voltage instead. So just be careful there, but since we know this is at the peak, these answers are consistent with themselves, so this means this is done. This question is good to go. Well then, whew, that was the question. So I thank you for watching, and good luck with your practices, and Fat Mama Physics, signing out.